All right, thank you all. I'm pleased to be part of the Artemis team, and I want to drill in a little bit more into what we're going to be doing during some of those early human missions to the surface, and in particular, how we're planning the science and how we're, no kidding, planning what we're going to do during those missions. Wow, this is really sticky, whatever this is. So you've seen this slide before. This shows some of the potential landing sites near the lunar South Pole. We have teams looking at each of these sites in detail because each one of them is unique. Each one of them has slightly different illumination, slightly different communication to Earth. And we are, no kidding, really starting to plan this mission. So this is getting real, and it's a lot of fun. One of the things that one of our colleagues, John Gruner, I believe, may have done this analysis, is actually looking at traverses. How far from the Shackleton to Gerlach Ridge do you have to go to find some of the areas that are in shadow? And it turns out you don't have to go very far. You do have to traverse some pretty good slopes, but nothing really beyond our Apollo experience. I think we went up to about 15 degrees in Apollo. And so these are all within, the plausibility range of areas, PSRs, that we can get to with simple unpressurized mobility. So we are looking at opportunities for landing sites, for example, there on the ridge, and some of the interesting places we can get to. One of the other things we're looking at is mission planning, and in particular, when should you go? Through the databases we have from LRO, we have some really nice DEMs that have actually spawned a cottage industry of people who are looking at modeling the South Pole, the moon, and modeling illumination and things like that. And one of the things we've been able to look at is what areas near the South Pole are the most highly illuminated. If you were going with a solar powered mission, that would make a lot of sense to go there. And so there's that same ridge, and you notice that we have some areas that are 92% illuminated throughout the year, with only maybe a week at most of shadow. So this is interesting. I'm going to actually show you some mission planning data that we've been looking at. This is Shackleton Rim, and this is looking at 2 years. So one of the things we see here is there is truly at the poles a winter and a summer season. And the winter season has many long shadows, and you can see where those occur. And the summers have long periods of uninterrupted illumination. And in this case, if you're picking Shackleton Rim, this goes from 23 to 25. So if we were going to land in 24, you probably wouldn't want to land in July of 24 because that's in the middle of winter. But if you get to like November of 24 through February of 25, you're in that uninterrupted period of illumination. And so we're learning a lot about when we might actually be able to do these missions. All right. Now, this is going to be difficult for me to do because I need someone in the back to actually hit the animation button at the bottom of each of these. Okay, so here, these are actually two animations of the South Pole looking across an entire summer lunation. On the right is you're actually standing near the South Pole, watching the sun go around the perimeter, and if you could play the one on the left at the same time, they were generally synced. You could see you have Shackleton right in the middle of the image, to Gerlach off to the left, and you could see these shadows as they sweep by, and it's very interesting, the physics of this. Of course, every 29.5 days you have a lunation, and that same shadow sweeps by you, and it's either getting longer or shorter depending on what part of the year you're in. So the summer looks really good at the South Pole. Now, the next slide is the winter. Next slide is the winter. Oh, maybe I could do this. All right. So there we go. So we actually started just past Malapert on the right, and there's the sun going around, and we're at the South Pole. And the winter is definitely not as good as the summer. The shadows are much longer, and so as we look at actual times that we could send people down to the South Pole, it's going to be probably constrained to those summer periods that we talked about. So right here, there we're coming up on the Malapert peaks, and the sun goes away for a long time at that point. As you can see, the shadows of Malapert come around. So interesting analysis of what you can do. And so we've started to establish actual dates when we can go to some of these sites. Now, Marshall showed this chart, the charts on the right a little bit earlier. I wanted to dive in a little bit more about what we actually mean from these charts. And so we have Artemis Phase 1, which is really everything up to and including the initial human missions in 2024, and perhaps a second mission with the second lander in 2025. Prior to the humans landing, we're going to have a very robust Eclipse program. You're going to hear from Steve Clark about that in a little bit. And there'll be very robust robotic science and prospecting for resources. And if all goes well, we could use the Eclipse missions to perhaps pre-deploy some of the materials that we need for the crews that are going to come in 2024. And we've heard loud and clear from the science community that you guys want an unpressurized rover on the very first mission. Message received. So for that very first 2024 mission, you see we have unpressurized mobility, obviously EVA. There'll be robotically pre-deployed experiments. The Eclipse missions may actually be the way we deploy science instruments. In the lunar lander world, with humans coming down, you want to actually sort of maximize that mission just for the crew to come down and up, and it might actually be best to deploy the science instruments on robotic landers and have it all waiting for them when they get there. The other thing we're looking at is not just that 1 week that the crew is going to spend on the surface, but what happens in the 51 other weeks that happen after that. So we want to make sure we have assets on the surface that will continue doing science during the time periods the crews aren't there. Following that, we come to 2026 and beyond. Marshall talked just previously about the fact that there's been some talk about we're going to use the moon as a test bed for Mars, and then not think about the moon anymore. Nothing could be further from the truth. We are actually going to do some testing for Mars on the moon, but we're also going to be looking at a long-term human lunar surface presence. And it turns out when you put the things that you need for both of those together, the Venn diagrams have a whole lot of overlap in them. So you are going to see things like pressurized rovers, the need for cargo offloading and deployment and moving things around, ISRU first at the pilot scale and then scaling up, permanent surface power systems, permanent surface habitats. So all those will come in 2026 and beyond. This is our one of our sidewalk charts. It's just a way of showing where things get deployed. In this one, I think I showed the pressurized rover as early as 2026. That depends on a lot of factors. We know that in order to get the crew size up, we have to have some place for the crew to live on the surface, and a crew of 4 can't live in the lander. So the pressurized rover may come in 2026, may come a little later, but we know until you get things like pressurized rovers or permanent surface habitats down, that the crew size can't go up until you have a place for them to live. So this shows the basic program. Eclipse landers initially, perhaps landing a small unpressurized rover for the crew prior to the 2024 crew mission. Then you start seeing crews of 2 After that, you start seeing ISRU pilot plants and pressurized rovers come in at the end of this. And then the future, of course, we're still working on. But the important thing is we're giving a whole lot of thought to 2024 and what comes in the couple of years after that. All right, I wanted to use these three charts, which were given to me some time ago by Sam Lawrence, and I hope I don't embarrass Sam by showing him his own charts back. But Sam is helping us a lot to establish the science goals for the 2024 mission. And I wanted to show these because we take these very seriously. We hear the science community talk, and we know what kind of things you want to do. So we have these key science questions that have come from the 2007 NRC report and from some of the recent strategic action teams and the April workshop, I believe. And, you know, the key science questions that you guys have defined are the key science questions that we want to help put a mission together to help answer. So all of those that you see in the NRC report and which are important to us and which are basically sound like the breakout groups from this workshop are the science missions that are the science questions that we're going to help you answer. So for the 2024 mission, first step is you know, a mission that may go up to 6.5 days in duration. 2 crew, so you have 2 crew members out on EVA. It'll be mainly geological exploration. We hope to have an unpressurized rover there. We will be able to bring some instrumentation down on the lander, and we hope to have other instrumentation, other science experiments we could pre-deploy on robotic missions. And so it will be a very robust mission from the very beginning. And that's what we're hoping that for the 2024 mission, we have a very robust science program, and we hope that you guys will help us define the details of that. And Sam was, he gave me this one page to explain the benefits of an unpressurized rover, just in case I didn't understand it very well. But I think we all understand that mobility and the added science you get as you add mobility to the system is, you know, go hand in hand. So we're absolutely going to try to get mobility on from the very beginning. All right, and as I'm counting down here, 20 seconds to go, I wanted to end with one picture, and I thought this was interesting because we have some new graphics coming out of NASA, and our graphic artist put this together, and I thought it was a good picture. It's a notional lander in the background, but it shows an astronaut in a new EVA suit, which has much more flexibility than the Apollo EVA suits, and when I asked our artist, I said, this is a great image. Where did you get the idea of showing an astronaut deploying geophones? And he said, what's a geophone? So with that, thank you for giving me 15 minutes. And if you have any questions. Dr. Epler.
Yes, sir. Dean Epler, Aerospace Corporation. We always show pressurized or unpressurized rovers as LRV kinds of things. And that's not bad. LRV was a great vehicle. But we have other ways of doing it now, like segways that are lighter and potentially just as mobile. I'm not saying don't use the LRV, but I think there are other ways to get around now that may reduce the down mass and still provide the same capability for both crew members.
All right.
So
yeah, thanks, Dean. And we are looking at options. We want an option that works not only with the crew on board, but also is your robotic platform for that other 51 weeks as well.
Hi,
Yes.
Carly Peters, Brown University. Very exciting discussion, lovely projection. One thing that no one has mentioned yet this morning, which is a bit surprising because it's been such a core of this community, is samples. The sample return that has kept this community alive for the decades that we haven't done anything. Could you say a little bit about that?
There will absolutely be samples returned. Now, the quantity is really the only question. You will have, as we showed, perhaps up to 6.5 days, which could be maybe 4 EVAs to collect samples. And so you can obviously collect a lot of samples in that time. What will likely be limited by is the amount of mass we can send back to Earth, not only by the ascent stage of the lander, but by Orion coming home as well. And I think Greg is going to talk a little bit about that in his talk about what sample up mass will be. But yeah, obviously it goes without saying that we're going to do sample collection. I'm sorry for having assumed that. Yes.
Brad Jolliffe, Washington University. Carly asked my question, so I'm just here to emphasize it. But I'll add that, as you remember, back in constellation planning, we didn't take it for granted that there would be plenty of return mass capability for samples. And so there was actually quite a bit of effort on this part of the science community to say, samples are still important. There's a lot of things we can do on the surface and in situ, but we still have a lot of things we can do with samples. And so I just want to emphasize that. And in constellation times, we were arguing that the return mass allocation ought to be at least as much as it was for Apollo 17. And that was quite a struggle.
All right. Thanks, Brad. Yeah, I know that. And I know we're going to do everything we can to get as much sample return mass as we can. It's really the physics we're fighting against. And so we'll do the best we can. Yes.
Mike Siebert, Colorado School of Mines. On the chart with the notional use of ISRU and after 2026, specifically what resources are being looked at for those pilot ISRU systems?
So right now, and I don't think we have anyone from NASA's technology group that's going to speak. Yes, we do. Okay. And tell me if I'm wrong, but typically we're pursuing both paths right now until we know more about the state of volatiles. So until we know whether we have volatiles in useful quantities, we are pursuing technologies for both volatile ISRU and regolith-based ISRU.
And I think kind of a quick follow-up was using regolith more as a civil engineering tool and less as a consumables source. So that was part of the consideration as a resource.
I'm a big fan of pushing regolith around myself. Thank you. All right. Thank you very much.